Hi. One question that's interesting to consider is, how old is the universe? How would we determine how old the universe is? Well, one way to determine how old the universe is based on a cosmological model. If we have an idea that the universe starts off as a highly compressed state, expands outwards, and gravitationally everything slows with the expanse of time. If we measure our current rate of expansion, called the Hubble constant, with the right cosmological model, we can predict how long it would take for everything to coalesce back to its initial starting point. Well, when we do this using the limited expansion model, which includes all that dark stuff, the age that is determined for the universe is about 13.7 times 10 to the ninth years old, or in American terminology, 13.7 billion years old. And it's with an amazing amount of confidence that they state that we're finally zeroing in on the age of the universe based on the percentages of dark matter and dark energy. And there are no issues. Everything is falling into place. Well, you're only hearing part of the story. There's a whole group of people who have written papers that have determined that the age of the universe is actually older than this. And the people that have done this are people that are working on the evolution of stars. And now, when you listen to the modern cosmology groups, they'll say, oh no, that issue's been all resolved. See, there's these papers that have been written, and they can pull out some paper that conforms to their model. But it is not the majority consensus. It is not what most of the stellar astrophysicists have determined for the age of stars. And on this list, I did a research study on how old stars have been, starting the age estimates, starting in 1982 and went all the way up to the year 2003. That's when I compiled the information. And during this time period, there were 116 papers based on the age of stars and globular clusters. 77% of them all had ages that were greater than 14 times 10 to the ninth years old. These stars are older than the age of the universe. Now, it is an amazing thing that they could even discover this or estimate this. And how it is done, what they do is they look for stars that are in groups called globular clusters. And these clusters are distributed within our galaxy. And they tend to have all the same chemical characteristics, which kind of gives the impression that they all were more or less formed at the same time. And these stars tend to have a range of masses. And when they reach a certain point in their evolution, they change rather dramatically. They turn into red giants. And the process that they've been able to figure out is this. A normal star, such as our own, will consume its fuel within the core of the star. And as the hydrogen is converted into helium, the fusion process occurs. Eventually, all the fuel within the core of the star is consumed, and fusion stops. At that time, the star starts to cool, and at that time, the star also will start to collapse. There's no more source of high energy increase in temperature causing the star to envelope outward. Now, the star is going to start to compress and contract. Well, what's happened, the mass of the star is tremendously huge mass, and as this mass comes slowly crushing back in, the temperature rises again, and we get a second phase of initiation of fusion occurring again. But this time, instead of it's outside the core, it's within kind of like the inner parts of the atmosphere of the star itself. And this new phase of fusion causes the star to suddenly get very, very big, the red giant phase. When our star goes through this phase, it believes it will expand outward and include the orbit of our Earth. The Earth will become toast. But this departure, and it's observed in globular clusters and throughout our galaxy, and even in other galaxies, this transition to this is a very dramatic change of state. So you can say, at this time, the star has changed. And when they figure how long it would take for this process to occur, the age is all longer than the age of the universe itself. In fact, the problem is even worse, because when they do these calculations, they start with a star of a certain size, and then they figure, and they don't even include the formation process. How long would it take for the star to become this? If you add another 500 million years to all those numbers, none of them fall within, or very, very few fall within a reasonable approximation to the age of the universe based on our modern cosmological model. So now, why was I interested in this? Why was I looking for this kind of relationship? Well, the effect of gravity is a function of time in my model. So in the past, if stars were experiencing a greater gravitational force, they would evolve more quickly. This is something I should observe or should be seen. And this is exactly what the model, so a prediction of my model is being found in observation. So now, I'm not done yet. There are a whole long laundry list of other issues that exist that will be addressed in my future videos. I look forward to sharing them with you, and thank you so much for your time.